My colleague Jens Monk is here. I'll talk a little bit about low Earth orbiting satellites. 35 years ago, we had this crazy idea. It seemed like science fiction at the time that we have these constellations of satellites orbiting over us, providing service anytime and anywhere. And the thing I noticed about this graphic was that the artist thought that penguins live at the North Pole. Well, it's not true, of course, but we do have LEO satellites nowadays and lots of them. And so that's what Jens and I are going to talk about. First of all, a little introduction. The difference between a low Earth orbit satellite and what we call a geosynchronous Earth orbit or geosatellite is basically altitude. The geosynchronous Earth orbit is at 36,000 kilometers over the equator, or 22,000 miles. Anybody know why they use that particular altitude?
Synchronizing the Earth.
Right, it's synchronized with the rotation of the Earth. So the satellite goes around once every 24 hours. The Earth goes around once every 24 hours. And so that's why most of the satellite Earth stations you see don't need to move, because they just need to look at one place in the sky. To scale, this just gives you an idea of the great difference between those altitudes. The geosatellites are between 500 and 2,000 kilometers. So there's a very great difference. And that means that the delay that you experienced, anybody ever talk on a telephone call that was going through a geosatellite? Lots of delay, right? But that's not the problem with LEOs, because there is a little bit of delay, but since their altitude is so low, the signals don't have to travel so far. So there's also not so much delay. Also, it's much more feasible to do mobile or portable service because the path length is less, so you don't have a lot of signal attenuation. And with a lot of satellites, even they're going around and around, you can still cover all points on the surface of the Earth, especially if you use what we call polar orbit, which means from North Pole to South Pole. And this animation illustrates how you can cover all of the Earth with a constellation of low Earth orbit satellites, even though they're going around the Earth about once every 20 minutes. This is actually the Iridium constellation, which is an older one, but it illustrates the point that you can cover the whole Earth with a constellation this way. So I'm going to, just a little bit of terminology, I'm going to talk about orbital inclinations. The inclination of a satellite orbit is the angle between the orbital plane and the equator. Or you could just think of it in two dimensions, where the equator is represented by a horizontal line and the satellite orbits are represented by those other lines. So orbital inclination is just the angle between the equator and the orbit. And there are three examples that are shown there. I'm also going to talk a little bit about frequencies. The new LEO satellites are operating some at Ku band. This is a pretty high frequency. This is higher than most of your cell phones are using. Ku band means that the transmission to the satellite up goes at 14 gigahertz and down at 12. Another band is Ka band, similar story, up at 30, down at 20. And all the constellations I'll be talking about are using one of those two bands. But V band has also been allocated for this service, and that may be used in the future. That's up on 50, down at 40. Know anybody that's on Starlink? No, I was pretty sure you do. There are lots of Alaskans now, especially out off the grid, that are using Starlink for their broadband service now. So this is what a Starlink satellite looks like. And these are kind of the specs. There are about 8,000 of them that are in orbit. They have authorization for a total of 30,000, and they're planning about 42,000. I'm giving you the altitudes here. They've got a number of different altitudes in that range between 279 and 570 kilometers, 4 different orbital inclinations. And for their user links, that would be the radio link from the satellite to the user and back. In this case, it's a KU band. And Starlink also has inter-satellite links, which means the satellites can talk to each other. And those are either a Ka band or they're optical, they're laser links. So you've got satellites talking to users on the ground, and you've got them talking to each other, right? Why do they need to talk to each other? The reason is to reduce the number of gateways that are needed. So with those inter-satellite links, a transmission goes from a user to a satellite, and then it's relayed satellite to satellite until it gets to a place where it could be downlinked to a gateway on the ground, which is how it connects to the internet, right? So you've got user terminals, and then you've got gateways that are connected almost certainly by fiber optic cable to the core internet. So that's why you need those inter-satellite links. Starlink started off at Ka band, but now they're migrating to optical. This is what you get if you're a customer. Are any of your customers? Look pretty familiar? Yeah. And so they, you go online, you put in your order, they ship it to you and install it yourself. And how did that work out for you? Okay.
Yeah, you live on North Slope.
And no human contact, right? But you never talked to a person, right? So that's how Starlink works. The antenna is about 50 centimeters by 50 centimeters, and that's what it looks like on the rooftop. Another company is OneWeb. OneWeb is also already in operation. That's what one of their satellites looks like. They only have about 650 satellites at a higher altitude, 1,200 kilometers. And their orbital inclinations are 90 degrees. Now, a 90-degree orbit, that's the polar orbit that I talked about before. Some of these other ones aren't necessarily polar, but the lower inclinations will still cover most of the population of the world. But OneWeb chooses to use a polar orbit. Their downlinks to users are Ku band, and they do not have any inter-satellite links. They are what we call bent pipe. So what that means is that for a satellite to provide service, it has to be seen by a user terminal, and it also has to be seen by a gateway. And so it has to go to a user, up to the satellite, and down to the gateway. So you can see how you need more gateways with this story than you do with inter-satellite links. That's what a OneWeb antenna looks like, pretty similar to the Starlink. Now, a couple of other companies that are not yet providing service, but they will soon provide service. And this one's been in the news. I bet you've read about it. Amazon. They call their system Kuiper. And they so far have only launched a few more than 100 satellites, but they're authorized for 3,200, and I'm pretty sure there will be more and more after that, because these are the big guys. Amazon is Jeff Bezos, Starlink is Elon Musk, right? So it looks like this is going to be the big competition, but these guys are a little bit late getting started. So you can see their altitudes there, their inclinations, and their user links are at Ka band at the higher frequency, and their inter-satellite links are all optical. And then, they actually offer 3 different antennas to users, 3 different sizes there. And the bigger the antenna you use, the better performance you're going to get. That's what it comes down to. And then the last one is Telesat, which is a Canadian company. And they're also just getting started, planning to begin launching next year in 2026. About 200 satellites initially, then 1,600 after that. And you can see they've got 2 altitudes, which are higher than some of the others, 2 orbital inclinations, and also user links at Ka band and optical inter-satellite. Now I want to come back and just make a comment about these flat panel antennas, because I'm going to be talking a lot about beam steering, about these antennas steering their beams, right? And you may be familiar with beam steering, or one way to kind of think about beam steering is, in the old days, you had a TV antenna on your roof, right? And you might be in a rural area where you had TV stations on the same channel in cities in different directions. The way you could solve that problem was with the antenna on your roof, you could point it at either city A or city B, right? And if you did that, you would be getting signal from whichever one you were pointed to. So you're effectively beam steering. These flat panel antennas can also do beam steering. It's kind of magical because they don't move. They just sit there, but they're still steering their beam to look at different satellites. Because as those satellites move across the sky, you've got to track them, right? And so the way they do that is with beam steering. And my distinguished colleague is going to explain in just a little bit how they do that. But in the meantime, there are some issues. This is all good service. People are pretty happy with Starlink. I talked to a lot of people. I think there are thousands of people in Alaska now that are using Starlink. There's really a pretty large number. And so people are happy. But there are some problems. There are some issues. One issue is light pollution. These satellites, when they're on their way to orbit and when they're in orbit, reflect sunlight. In fact, there's a series of Starlink satellites on their way to orbit. I would have to admit that this slide exaggerates a little bit how bright they are. But they're bright and people can see them. And people that live down in the South 48, a lot of them have told me, you know what I saw in the sky? You know, when they saw this line of satellite, about 60 of them, because that's how many they launch at once, right? And they're reflecting sunlight. So the optical astronomers aren't very happy about that. And they're doing some negotiation. Starlink has made some changes to design their satellites so they don't reflect quite as much. And I will say that once they're in orbit, they're not as bright as this. So they reflect a lot of light when they're on the way to orbit, and that's what people see with the naked eye. But after they're in orbit, they're not reflecting that much light, but they're still reflecting enough light that it's causing some problems for the astronomers. So that's one problem. Another problem that you might have thought about when I started talking about all these thousands of satellites up there is the space junk problem, right? With all this stuff flying around, some of it at roughly the same altitude, it seems possible there's going to be a collision. In fact, there was a movie about that. It was Gravity. Did you see Gravity? In Gravity, that was where there was actually collision and debris was flying and there were these astronauts at the space station. And so that kind of illustrated the problem. Well, NORAD, the North American Air Defense Command in Colorado, is tracking all this stuff. And they can see objects, I think, down to about 10 centimeters. So they know what's going on up there. And they make that information available. And so satellite companies are actually steering around each other when they see that, that there may be a collision. And I guess one little story from the past, there was actually a collision back in, I think it was in 2008. Iridium, the older company that provides cell phone service, noticed that one of their satellites had disappeared. It was in service, it just disappeared. And after some investigation, it turned out that it had collided with a Russian satellite. And so that kind of illustrated the problem, I guess. Now, Iridium has spare satellites, so they were able to move another satellite into position, but that was a collision, and there have been other collisions too. The one that everybody worries about is what's called the Kessler effect, which is where there's a collision, it throws off debris, then that causes other collisions, more debris, more collisions. That's the doomsday scenario. That's the one that we like to avoid. And that's the one that some other folks are working on figuring out when we get to a point of what you might call critical mass, right? So how much more stuff can we put up there before we really have this kind of a problem? So those are a couple of issues, but the one that Jens and I and some other colleagues have been working on is the radio interference problem. The radio interference problem. And there's the potential for interference between LEOs and GEOs, and also between LEOs and other LEOs. Why is that a problem? It's a problem, it's a potential problem because these satellite services are all assigned in the same spectrum. And they're not assigned in their own channels like you would expect. They're actually literally in the same spectrum. And so that's why there's an interference problem. The regulators have something to say about this. The regulating agency in the US is the FCC, the Federal Communications Commission. And then there's an international one called the International Telecommunications Union. That's part of the UN. But both of these have the same requirements at KU and KA bands, which are the ones that we're interested in. And the idea is that the GEOs have been around for a long time, decades, right? The LEOs are the new kids on the block. So the regulators say that the GEOs have priority. The LEOs must adapt to make sure that they never cause interference to these existing services that have been there for a long time. So in the terminology is that the GEOs are primary and the LEOs are secondary. The LEOs must design their systems so they don't interfere. So that's one problem that we have talked about. Even though even though that requirement is in effect, there is a proceeding going on right now before the FCC where Elon Musk actually wants to change those requirements. But we don't know how that's going to come out. It could take years. So for this conversation, I just wanted to talk about the existing rule, which is the one that I just described. So let's talk about how interference could happen, how a LEO could cause interference to a GEO. And people like to talk about an inline event. So if you have a GEO Earth station in communication with a GEO satellite, you see here, and those two are going around together like we discussed. In the meantime, here's a LEO satellite that's coming around about once every 90 minutes, but it's one of thousands of satellites. So it stands to reason that at some point, that LEO satellite is going to be in a position right between the GEO Earth station and its satellite. When that happens, that's an inline event, and there is at least the possibility of interference. So here's the same picture. You've got the GEO satellite, the LEO satellite, and the GEO Earth station all in line. Now, the GEO satellite is pointing straight down toward its Earth station. And if the LEO satellite is always also pointing straight down, and if they're transmitting on the same channel or in the same bunch of spectrum, then looks like interference, right? So that's a problem. But the LEO satellite is required to not let that happen. What about if the LEO satellite is over here? Will that LEO satellite, so it's not exactly in line, but it's almost in line. So do you think that would cause a problem? Well, it depends. So the answer is maybe. One problem with this kind of a drawing is that radiation isn't really confined to those lines that I'm showing you, right? That's just the center point, right? But the radiation actually spreads out over distance. So a better way to think of this is to think of that radiation as a cone. The cross-section of the cone gets bigger with distance. So if we showed the cone that represents the radiation from that LEO satellite, and if it intercepted the geo Earth station, then that would indicate that there's potentially a problem. All this depends, of course, whether they're transmitting on the same channel or in the same part of the spectrum as the geo Earth station. But practically speaking, it's not completely practical to even know where all the geos are, what frequencies they're using. There are many geos up there, right? And if I'm a LEO, I have to protect all of them. So it'd be better to come up with a foolproof method, which is going to be beam steering, in order to avoid. If you steer your beam properly, then you don't need to worry about what channel you're on, because you know you're not going to cause interference regardless. So we'll talk about two kinds of beam steering that the LEOs need to do. Beam steering by the Earth station and beam steering by the satellite. Beam steering by the Earth station, so they don't cause interference to the satellite. Remember, the satellite's both receiving and transmitting, and interference by the satellite, so it doesn't cause interference to the Earth station on the ground. So first of all, let's look at the LEO Earth station, right? The LEO Earth station doesn't want to interfere with any of those geo satellites that are up there. The geo satellites, as seen from any point on the ground, are all along an arc. We call it the geo arc. It's the circle that's 36,000 kilometers above the equator, right? Then if you see that from some other point on the Earth, it looks like an arc. So if you're a LEO Earth station, don't point your beam toward that arc. Sound right? Don't point your beam toward that arc and you won't cause interference, except what about that cone? So it's not just a straight line, it's a cone that goes out, right? So to allow for that cone, we need to allow a little margin on either side of the arc, right? And so that's why I put those green lines in there. So the rule is, don't point your beam anywhere inside that so-called forbidden zone. So that's what you need to do from the Earth station side. From the, from the satellite side, what you need to do is just need to do what some people call look aside. Just point your beam in another direction that's not toward that geo Earth station. Okay, sound good? So that is the whole story that Jens and I have written about in a paper. I don't know how many of you are interested in following up, but I'm going to show you these references, these papers that we've written. I'll summarize them at the end. So this will come back, but the paper is about the feasibility of steering the main beam, steering the beam of the satellite and the Earth station to avoid interference. And that's all on the subject of LEO to GEO interference. Okay, so I talked about the radiation is not a straight line, it's a cone, but even the cone oversimplifies the problem. So now we'll take it another step. Here's an antenna pattern of a real antenna, and this could be a parabolic antenna, like the Earth station used to see around, or it could be a steered beam antenna that Jens is going to talk about. And you can see that most of the radiation is to your right there. That's the main beam. But the way these antennas work is they also have radiation in other directions. It's not as much radiation, but there's some. And so there's the main beam, and then there are all these other beams, and we call them, in the jargon, we call the main one a main lobe, and we call the other ones side lobes. The radiation from the side lobes is weaker, substantially weaker. This is on a logarithmic scale, so they're actually much weaker than the main lobe, but they're still there. So if they're so weak, just like when you were pointing your TV antenna toward that one station, and you might get a little weak signal from another station off to the side, so that's not to be a side lobe. It's not a problem, because it's so weak. And that is true here, depending on how many satellites are up there. But let's just come back and get back to the main point here. The satellite has an antenna pattern with a main lobe and also with side lobes. The Earth station, let's say it's receiving, it has a main lobe and then it also has side lobes. So even if the LEO satellite is pointing, in this picture, is pointing straight down, and the GEO Earth station is pointing straight up, it's still possible that you could get side lobe radiation off that LEO satellite in a direction that's within a side lobe of the GEO Earth station. It's possible. It would be really weak, but it could be there. And so if we go back to this picture, it's not so simple, right? You know, we pointed our beam to the side, but we also have side lobe in the direction of the GEO Earth station. It's not a problem. It's not a problem for one satellite. But if you have thousands of satellites up there with thousands of side lobes, it all adds up and it could be a problem. Well, we've written an article about that too. And in this article, we talk about what we call side lobe suppression, which is there are ways which Jens will describe to reduce the level of those side lobes below what I showed you, right? And so you want to do that, but depending on how many satellites you have up there. So if you only have a few satellites, you probably don't need to worry about side lobe suppression. If you have thousands of them, and that energy can all add up, then maybe you do need to worry about side lobe suppression. So this paper that we wrote talks about side lobe suppression as a function of the number of satellites that are up there. So we actually have a graph in there. If you have the x-axis is the number of satellites, the y-axis is how much you need to suppress your side lobe. And that's that second paper, which I'll also put up at the end. So that was all about LEO to GEO. Now let's do LEO to LEO. This is where it gets really interesting. First of all, you could have LEO to LEO interference within one constellation. So Starlink has 8,000 satellites that will have 30 or 40,000, right? Those satellites could potentially interfere with each other, depending on how you design a system, but it's possible. So that would be the problem of intra-constellation interference. And then the other problem is Starlink could interfere with OneWeb because they are all in Ku band, right? If Starlink someday, and I think they will move to Ka band, then you've got Starlink and Amazon trying to coexist within one piece of spectrum. How do you solve the problem? Work it out, guys. That's what the regulators say. Work it out. Down on the bottom of the slide there, it says the FCC says, please work it out among yourselves. If you don't work it out, we've got a default, but you won't like the default, so work it out among yourselves. Okay? So how are they going to do that? That's what we're working on. We don't have the answer quite yet, but we're working on it. So a little bit more about LEO to LEO interference. In this picture, and this is intra-constellation, so this is just one constellation. But you might remember from the earlier slides, even in one constellation, we have satellites at different altitudes, right? Different orbits. So in this story, we've got satellite A talking to Earth station A, and then at a somewhat higher orbital altitude, we've got satellite B1 talking to B1 and B2 talking to B2. Will B1 interfere with A? Well, we talked about, that's just the same picture we talked about before. Depends on the cone, right? It depends on the actual antenna pattern. But satellite B2 is pretty far away. It's pointing to a different spot on the ground. So it doesn't look like there should be any interference. Except if you think about the side load. Right? So this is a pretty similar story. Now it looks like, well, satellite B2 maybe is sending radiation toward Earth stations B1 and A, so it could conceivably be sending radiation into both of those. And that's what we're working on at the moment. What this tells a LEO operator is they can avoid this kind of inter-satellite interference by thinking about the main beam and the side lobe of a receiving Earth station, the main beam and the side lobe of the transmitting satellite, and are they still on the same channel? Now, I said, in the case of the GEOs, I said, well, you practically, you don't even know what channel they're on. But now these guys, they do know what channel they're on, because if it's one constellation, it's one company that's doing this, right? If it's two companies, then they probably need to coordinate to make it all work out. So you want to avoid this situation where you're sending radiation through either a main beam or a side lobe, and receiving through either a main beam or a side lobe, and if you're on the same channel. And there's also something called polarization diversity that I haven't talked about here, but that's another thing that could help with this. But anyway, this is what we're looking at now. And at Carnegie Mellon, we've put together a simulation. So now you can imagine this is really complicated, right? Because you've got thousands of satellites up there. They're steering their beams in different directions in order to serve customers in different places. And we're trying to get a handle on how you would mitigate this problem. And the problem gets worse and worse as you have more and more satellites. And we're just starting to work on this. So I'm giving you kind of early stage information. But we're looking at 4 different cases here. The first case is intra-constellation, just one constellation without any mitigation. In other words, just point your beam wherever you need to point a beam to serve a customer, and don't worry about this problem. What kind of performance does that yield? Then if we work on mitigating the problem, then how much will that improve the performance that the customer actually receives? And then with all that in mind, if we get that one figured out, then we can go to the inter-constellation, say Amazon and Starlink, and how do we do mitigation so we don't disrupt the other guy? So that's what we're working on. And this is a pretty big simulation where now we're starting to think we might need some supercomputer time to run this. But we have some knobs that we can turn to create various scenarios. We can put in lots of details about the orbits. We can put in the orbits themselves, the number of satellites, the antenna patterns, what do we need to do about side lobe suppression. We can simulate at either KU or KA band, and we can specify the households and where they are that we're trying to serve. We could just serve everybody in the United States, or we could serve some subset. And the result of this simulation tells us the speeds that are experienced by all the households as a function of the settings that we've done. And so now this is some breaking news. This is just an early result, but so we've run the simulation and we've run it in a way that tells us the speed that an individual household will experience with 95% confidence. And we've run it for Starlink's first generation constellation. So that was about 4,200 satellites out of it. So we're not running it yet for the whole constellation, but for partial constellation at KU band. And we did use 30 dB side lobe suppression. And the households that we've chosen are rural households, because it's kind of obvious that this is more of interest in rural areas, because urban areas typically have fiber optic cable and they don't need this. So the definition of rural there's kind of an official definition of rural, which we've chosen, which is 100 people per square kilometer. So here's the result. This is the simulation result. I have to point to the scale down here. So can you see the scale? Green, yellow, and red. So the green numbers are around 100 megabits per second. That's pretty good, right? That's on the downlink. The yellow is around 50 or 60, and the red is around 15 or 20. So what this is telling us, and this is looking at all rural households in America, in the 48 states, the eastern part of the US is getting around 15 to 20 megabits per second. The Midwest around 50 to 60, and the same for the West, except there's a few little pockets in the Rockies there that look like they get 100 megabits. So why do you suppose there's such a big variation? Any ideas?
Population density.
Exactly, population density. Right, so there's a lot higher population density. You can see the variation here, but in general, there's a lot higher population density in the East than in the Midwest and the West. There's only a certain amount of capacity in the constellation over a certain part of the country, right? So whatever number of households are sharing that capacity, that's going to determine how much each household gets. So it's population density that explains this, and it's what we expected. But what we need to do now is need to ramp this up for bigger constellations. We need to start looking at mitigation methods and so on. And we did also run this for Alaska. There's a lot of nothing in Alaska. But you do see the green dots there. Those are villages, right? So you have households and villages, right? And they're getting pretty good service, right? So that tells us that, this looks like a pretty good technology for rural Alaska. Well, no big surprise. The people in rural Alaska have figured this out, right? So that's why there are so many of them out there that are using Starlink, primarily Starlink. And so I'll put these references up at the end, but there's a conference paper that's going to be presented next week, or next month rather, in Canada. And so then this paper will be presented. And I'm now to the point, I know you really want to know how these flat panel antennas can steer their beam. That's what Jens is going to talk. It's your turn, Jens.
Okay, thanks, Alex.
Bottom fell off this, but it's not a problem.
Okay, so this is,
The right arrow goes forward.
okay, how do I go back the other one?
Yeah, put that.
Antennas, radiation patterns matter. I didn't really need to put that in there. So I want to show you some examples of actual radiation patterns. So I have two examples here. One is from a 4 wavelength aperture antenna, for example, a parabolic dish antenna like the one shown here. Same thing for an 8 wavelength aperture antenna. And the important thing that I want to note here is when we talk about the size of the antenna, we usually talk about how many meters is it, but really the important thing is how many wavelengths is it, okay? So if something is a 10 wavelength diameter antenna, doesn't matter what the frequency is, it can be 1 meter or 10 meters. If it's 10 wavelengths, it has the exact same radiation. So the one thing we're going to notice is that as you increase the diameter of the aperture in terms of wavelength, look what happens, it gets narrower and narrower. And we would call an antenna like this more directional. The power is more focused, so that arrow that Alex showed in some of the sliding going from point A to point B. This is more directive. So more of its energy is in the main beam. And what I'm plotting here is actually the power density of the radiation pattern. What we also showed in some of the slides is these side lobes that you don't see here because this is a linear scale. So what I'm going to do next is show you the exact same patterns in a dB scale, and you can see all of a sudden, okay, here's all these side lobes. So if I do that, I get these patterns here. So this is exactly the same antenna I showed before, 4 wavelengths diameter. It looks a lot broader than it did before. Here's the 8 wavelength antenna, and I've also included 16 wavelengths and 32 wavelengths here. And you can again see how the main beam becomes increasingly focused as the size of the dish in terms of wavelength increases. And now here we do see the side lobes, first, second, third, and what we notice is the bigger the dish in terms of wavelengths, the more side lobes there are. But what we maybe have to look a little closer to see is that the level of the first side lobe is always the same. It's 17 decibels below that maximum. So in all cases, you're 17 dB down. It's just that this one occurs closer to the main beam than it does over here. And I should also say, why does this look so much fatter than before? So if I go back to the previous slide, sometimes we talk about the beam width, when we talk about the cone, where's the energy going? We talk about the half power beam width. So if you look at this is a linear scale from 0 to 1. So let's see, there's 0.8, 0.6, so 0.5 is about it here. So if I draw a line right through there and measure that angle, that's going to be what we call the beam width of the antenna. So half of the energy is within that beam width. And once you get outside of that beam width, the energy density drops to less than 1/2 of its maximum. And the same thing here, you can see that this thing has a narrower beam width. Okay, and we would say this one's also more directional. The energy is more focused. So if we go back to this here, that half and power beam width, we now refer to the 3 dB beam width. And if this is 60 dB, this is 40 dB, 3 dB down is this little wedge right here. So that angle ends up being exactly the same as it was before. It's just very exaggerated in this figure here. So here's kind of a plot, not a polar plot, but a plot of radiation patterns for dish antennas of various sizes. From, I said, the distance in meters doesn't matter, but I'm telling you that this is KU band, so this is going to be 12 gigahertz. So KU band has a wavelength of about 2.5 centimeters. So even 0.6 meters is 20 some wavelengths. It's very focused. And you can see that as the dish gets larger in terms of its diameter in meters, if we keep that wavelength the same, you see that the beam width keeps getting more and more focused. We have the last one's this 10-meter dish at KU band is enormous in terms of wavelengths, several hundred wavelengths, I think. And you get this very, very focused beam width. So one of the things I just want to point out in this slide is that first side lobe is always right there at minus 17 dB. And this is what you see with circular aperture antennas. Okay. So what I want to talk about are phased arrays and why we might want to use a phased array instead of an aperture antenna. One of them is the ability to electronically steer the beam. And if you have an antenna on a satellite and you need to steer that beam, a mechanically steered antenna is just out of the question. The other thing that a phased array allows is actually to steer beams independently in 2 different directions, more than 2 even. And finally, one of the things that we might want to do is control the level of those side lobes. So maybe 17 dB is too high. And we just have a lot more control when we're talking about phased arrays. So not all array antennas are phased array. There are also fixed arrays where they're not steerable beams. And I will tell you a little story about a fixed phased or a fixed array antenna that we were employing. Have any of you guys heard of the radar satellite? So it's not a communication satellite. It was scientific satellite launched by the Canadians. There was actually two of them. There was RadarSat-1 and RadarSat-2. But basically, it was a synthetic aperture radar antenna, and the purpose of the satellite was for studying the Earth surface processes. And one of the things they wanted to do was map sea ice in the northern hemisphere for shipping and things like that. But it was also for studying climate change and things like that. So it was a Canadian satellite, and it had a declination of 98 degrees. So it was beyond the North Pole. It was almost polar orbiting. It was a little beyond polar orbiting. But with the synthetic aperture radars, you have to look off to the side. So we actually use this satellite to generate an image of Antarctica. The problem is when you get to the southern hemisphere, that beam that was pointing towards the North Pole in the northern hemisphere is now pointing away from the South Pole. So there was this huge hole in our data. So if Antarctica is this big, the hole in the data was that big. So in generating this image, which by the way was published in National Geographic years ago, at some point we had to rotate the satellite, physically rotate it. So why am I bringing this up? Because if you have a fixed antenna, I mean, that's your option. You have to rotate the satellite to move the beam. So it was the very last thing they did because there was a small chance that we were going to lose the satellite because of this maneuver. It ended up working. But anyway, another reason to use phased array. In the case of these communication satellites, you're constantly steering. So phased arrays are your only option. So here's a picture of, a couple of pictures of some phased arrays. Here's one in a circular array. So you can basically arrange your antenna elements in a circular arrangement like we're showing here, or in some sort of rectangular square arrangement. This picture here is actually from the Starlink patent application for one of their antennas. So here you can see they also have it arranged in a circular pattern there. And there's good reason to arrange things in circles. So as I mentioned before, one of the things that we like about the phased array is the ability to steer a beam. And here what I've done is just change the phasing of each of these elements so that the constructive interference goes from being straight ahead. If your antenna array is like so, you're pointing your beam straight ahead. If you adjust the phase of each of the elements, you can make it so the constructive interference is in a different direction. That's what you're doing. So the amplitude of the currents, all your little elements are the same, but you're kind of delaying them in time a little bit so that the constructive interference is in a different direction. And I'm just kind of showing, you can go from no phase delay between the elements where you're going to get constructive interference straight ahead. And again, I think this is for 16 wavelength. So it's pretty highly directional antenna. Here we're steering at 20 degrees and at 40 degrees. But the one thing that you'll notice in this case is the level of the side lobes doesn't change when you steer the beam. Although the beam does tend to get a little broader as you steer it. So these are things you might need to think about as you're steering your beam. And in this case, the other thing you might not notice is for a circular aperture, that first side lobe is 17 decibels down. For a square aperture, it's actually a little bit higher. It's 13 decibels down. Your side lobes are a little bit higher. So that's a good reason to, instead of having your array in a square configuration, put your elements in a circular configuration. Actually, here's some plots my students made, which is kind of cool. So here's what the projection of a kind of a square array of elements, where I'm assuming that these element spacing dz and dy are the same. I don't know how many elements I have here. I don't remember. But this is what the radiation pattern looks like if you project this radiation onto a surface of a sphere far away from the antenna. And you can see that this right here is going to be your main beam, and these little smaller pieces here are all your side lobes. So that's gonna be your first side lobes and your second, third, and so on. And it's not really symmetric, the way it is. If you put them in a circular array, you get something that's more circular. The one thing you will notice when you do this, your main beam is a little fatter than it was before. So anything you do to help you in one area usually creates a slightly different problem in another area. Your beam gets a little broader. If you really needed that narrow beam, you're just going to need to make your array a little bit larger. But the really cool thing we can do is actually taper the elements. So instead of having all these elements have the same amplitude as far as the currents that we're exciting on them, if we taper it so that the amplitudes of the currents on these elements get smaller as we move outward, we can actually really reduce the level of the side lobes. And that's what I'm going to show next. So the antenna array gives us flexibility to electronically steer the beam and to adjust the amplitudes of the of each of the elements in our array so that we can taper it and reduce our side lobes at the expense of an even broader main beam, if you can see that. So here's a typical radiation pattern. This is for an 8 wavelength. I think it's a square aperture antenna here. Whoops, hold on. And here's the exact same thing with the tapered elements on the current. So what I'm doing is I'm decreasing the magnitudes of the currents on the elements in a Gaussian way, so that they're getting smaller and smaller out towards the edges and their maximum in the middle. So what you're seeing is what was minus 13 dB is now minus 35 dB. As a matter of fact, the second side lobe is actually a little higher than the first side lobe. But if I go back, you'll also notice how much broader it is now. So again, if you needed that narrow beam, you're just going to have to make your antenna larger. Okay, but again, we notice how much lower my side lobes are. So here's actually a plot that Alex provided from the people that he's working at CMU. And here again, they're kind of looking at tapering the aperture. So this first example here in blue is with no tapering. The beam is actually the narrowest, but the side lobes are also the highest. The second one here in green is with some tapering, and we basically lowered that first side lobe from minus 13 to minus 20 some, or minus 20 in this case. And the third example here is with the minus 30 dB suppression. And you can see that it has the broadest main beam, but our side lobes are really not down. So I had one more thing to show you. I think I can take questions if you guys have any. So one of the things you might think about when you're building an array is spacing of the elements in your array. And it turns out that the more elements you have, the more expensive it's going to be. So I mean, obviously, you're trying to optimize having fewest amount of elements without having too few elements. And I'll show you what happens if you have too few elements. So in this case, I have a 4 wavelength by 4 wavelength antenna, square antenna array. So it has, I think, 11 elements by 11 elements. They're separated by 0.4 lambda. And this is the beam width we get if everything is adding constructively. There's no beam steering or anything like that. Here's the exact same situation, 4 wavelengths by 4 wavelengths. But now I'm separating the elements by 0.8 lambda instead of 0.4 lambda. So almost, well, actually, what I have here is 6 by 6, so 36 elements versus 11 by 11, which is 121 elements, and it looks pretty good. The main beam here is about the same, so as long as everything is in phase and you're not trying to steer the beam, you're good. But look what happens when you try to steer the beam. This one, you're fine. So I want to steer the beam 30 degrees in a certain direction. Great, there it is. That's with a 0.4 lambda spacing. Do the same thing here. Oh, there it is, great. Oh, where's that? This is called a grading lobe, and it just happens to be that with that spacing, things add constructively in that direction, the direction you wanted. And then there's another direction where there's constructive interference. So this is not a side lobe. This is called a grading lobe, and these are awful. You have absolutely no control over these.
We had a question online.
Oh. Our side lobes. We'll do that at the end, yeah. Anyway, this is something I haven't talked about before, but if you want to be safe, 0.4 lambda, 0.5 lambda element spacing, you're good, and you can steer just fine with that. You're not going to have any issues with grading lobes. The one thing that people don't talk about a lot, though, is the impedance of your antenna does change as you steer the beam, and impedance matching is kind of important if you're an electrical engineer and you know. So just be aware there's something called scan impedance. So it's just another challenge. Okay, so I have one more figure to show, and this is a kind of a 3D picture of what I showed before, and kind of just a 1D slice. So again, here's the four wavelength by 4 wavelength array with the 0.4 lambda element spacing. See the beam shooting in that direction. And then same size array, but the element spacings are too large. And when you steer the beam, you're getting this grading lobe. You don't steer the beam, you're fine. So, you know, if you have an array that's not a phased array, that's a fixed, you know, 0.8 could be fine for you. You know, but if you want to steer the beam, you need to be aware of this. So anyway, and I had a question.
So, question was actually for you.
Okay, yeah.
The question was, and you might want to elaborate, was how are side lobes suppressed? So when I presented, I talked a lot about we need to suppress these side lobes. I think you covered it, but you might want to.
Yeah, I mean, side lobes are suppressed by tapering the magnitudes of the currents in your array. And so this is something you can't do with a parabolic dish antenna. And matter of fact, you know, even calculating the radiation pattern from parabolic dish antenna, there are assumptions, but you really don't have any control over what's going on. In order to calculate the radiation pattern of a dish antenna, you actually have to know what the electric and magnetic fields are in the aperture, which we can get to pretty good approximation, but you have no control the way you do with an array antenna, where you can adjust not only the magnitude, but the phase of each of the antenna elements in your array. So it's by gently tapering the magnitudes of the currents in your elements so that they go from maximum in the middle and gradually decrease out towards the edges, that you can suppress the side lobes. I hope that answered.
Yeah, I think that answers the question. And I guess to go back to kind of the big picture, the companies that we've talked about that are using these flat panel antennas, they're using them in both the satellite and also in the Earth state, in the user terminal, right? You saw the pictures of user terminals. So that means that they're actually using beam steering in both, because as the satellite goes over, it is pointing, and Jens mentioned multiple beams with a phased array antenna. That satellite is pointing multiple beams in different directions by feeding different signals at different frequencies to the elements, right? And then the ground station, the user terminal, has a simpler problem. They just have to track that one satellite. And so they're doing it using the techniques that Nick's described.
Is the grading lobe that constructive interference always at 90-degree offset?
No. It kind of all depends on that space, and matter of fact, if you made the element spacing like 1.3 lambda, for example, like really extreme, you would get grading lobes, even if you were looking directly straight ahead, because there's constructive interference in this direction. And then there's perfect constructive interference in two other directions. Okay, and you're just. Yeah, I mean, if there's like a one wavelength offset between each of these elements, they will add constructively again. Or integer multiples of one wavelength. So that's exactly what happened. And it's perfect constructive interference. So it is as big as your main beam. So yeah, you want to keep those elements close, obviously not too close, because you do have to worry about expense. 0.4 lambda and you are safe all the time. And if they're a little further apart, it can limit how far you can scan. So, as long as you don't scan too far, if they're 0.6 lambda, you could be okay. Yeah, you have to really know exactly what you need your antenna to do. So, any other questions?
Is there any kind of regulatory issue, grading load, like saying like, hey, you can't be doing that because you're causing interference, you're sending out signal and radiation to people that should be receiving it effectively.
When I worked for the FCC, this is whether the regulators would address such a question, right? They have very few engineers working there. They're all lawyers.
Yeah.
So they are more inclined to just tell you what the performance needs to be and leave. So I don't think the regulators are going to talk about grading loads.
I don't think it would ever get off the ground if it had a grading load problem. The engineer would have been fired probably.
I would hope for it, yes.
Yeah, I mean, it's kind of a well-known problem, so, yeah.
Typical spacing though is about half a wavelength.
Half a wavelength, that's still.
Any others? Was it clear? That's my question. This is the first time we've presented things in this particular way. And at the system level, we assume that engineers like Jens will do the right thing with the antennas, but we're trying to figure out at the system level, what are the measures that need to be taken in order to maintain adequate performance? Because if you're a user terminal and you're receiving interference, unwanted interference on your channel, then that's going to degrade the signal to interference ratio, which if you study communication engineering, that will degrade the performance. You probably still communicate, but maybe instead of 100 megabits per second, maybe you'll get 20 or something like that. So that's why we're working on it. No more questions from TV land, I guess. So, okay, I guess that's it. Thank you.
Thank you.
Thank you.
Yeah, that was your question. Oh, and maybe I'll put that back together.
Oh, right,
I should probably give it back to.
well, I have. Probably has to be safe. Yeah, I didn't think that's important. Oh, that'd be.
It's like going up there.
Oh. Oh,
All right, and the password for today's survey is challenges all lowercase.
Challenges.
Challenges all lowercase.
Where do you want it in here, Lemon?
Let me go check.
Pretty good contract rating.
Oh, yeah. Yeah, they're, we talked about it.
So one of the options that I will give you by mentioning.